Okay, so let's go on to talk about multi-class classification. This is the case where you have more than just two classes. Two classes is called binary classification. So basically, we will see that there are two approaches, one versus many or one versus one. We'll give some examples of both of these and discuss the pluses and minuses. So suffice it to say that there are many cases where you are interested in multi-class classification. You might have levels of credit riskiness. You might want to detect sentiment in more than just positive, negative terms. You might want to classify facial emotion into several different categories. So this is certainly a useful idea. Now, graphically, we can represent binary classification this way. If we have two features, we plot our data, we plot our classification. Each point will have one of two symbols. The multi-class would be similar. You just add another symbol for another class. And it's clear that I could do 4, 5, 6, 7, 8 classes and represent those the same way, just with different symbols. Now here we have one boundary between the two classes. In this case, it's not so clear. Where do you draw the line? Of course, you could draw one line to separate this class from these two, or this one from these two. So we'll see how to create separating boundaries in the multi-class case. As I mentioned, there's two basic approaches, one versus rest or one versus one. Okay, as I said, one versus many, one versus one. So what's one versus rest mean? Here's the steps that you go through. Decompose the K classes into K binary classification problems. You're going to create K separate classifiers. So in each classifier, one of the classes is chosen as y equals 1, and all the others are y equals 0. So let's see how this works for a 3-class problem. Since there are 3 classes, there's going to be 3 classifiers. There's going to be one classifier corresponding to each one of these 3 classes. So let's see how this works out. Here we have 3 pictures to show 3 different classifiers. In the first classifier, we're going to take this class to be the y equals 1. Right? That means we're trying to separate this class from all the other classes. Right? Now you can see that a separation would be something like this. For this case, we're going to take the class on the left as our y equals 1, and everything else is 0. So that's going to give me a classifier with a boundary like this. Finally, my third classifier gives me a boundary like this. Now, how would you actually apply this for a new data point? Well, suppose we have a new data point that actually belongs to class 3. We'll apply each one of these 3 classifiers to that new data point. And here's our new data point. It turns out that it's actually in class 3. Now, if I apply the 3 classifiers to this data point, you can see the first classifier classified it as 0, which means not in this class. The second classifier similarly classified it as 0, which means not in this class. The third classifier classified it as 1, so it's in this class. Now in this case, there's a clear winner. there's only one of the three classifiers that gave it a positive identification. But in many cases, the situation is a little bit more fuzzy. So we'll see how to deal with the data in that case. Remember that when we do the classifier, we actually get a probability. So for this new data point, we got a probability of being in class, in this class here. It turned out to be 0.01. Here it turned out to be 0.15. And here it turned out to be 0.97. So we can look at the three probabilities and take the one with maximum probability. And that can be our class determination. So we don't actually determine the outcome for each classifier. We compare the probabilities that are generated by each classifier and choose the classification that corresponds to maximum probability. All right? So here's a recap. Decompose the classes into k binary classification problems. Creates k separate classifiers. In each classifier, one of the classes becomes my y equals 1. Everything else becomes 0. Each classifier is going to give me a probability. Then when I take an unknown sample, I evaluate my h's for all my different classifiers, and I choose the classifier that gives me the maximum probability. Now the alternative approach is called 1 versus 1. And let's see how that works. Suppose we have a 3-class problem. Now we can develop a classifier for each pair of classes. That means we don't use the whole data for each classifier. We just take pairs at a time and develop a classifier for each pair. Now in this case, the number of pairs is also equal to 3. So we will get our 3 dividing lines, decision boundaries. Now suppose we get a new instance. Here's our new instance. We apply the 3 classifiers to our new instance. So in this case, we would get 0.48. This means that the new instance is slightly more likely to be in the class down here than the class up here. When we apply this classifier, we get 0.97. So the instance is much more likely to be in this class than this class. And here also, when we're comparing these two classes, the new instance is much more likely to be in this class than this class. So we're going to take these 3 results here and combine them. For example, the circle class. When I did this classification, this gave me a probability of 0.48 of being in the circle class. This one did not evaluate the circle class. This one gave me a probability of 0.01 of being in the circle class. So I'll sum these probabilities from the 2 different tests that did involve the circle class. Now clearly I can do the same thing with the triangle class and the X class. For the triangle class, you can see that in this case, the probability of determination was 0.52. In this case, the probability of determination was 0.03. So my total, or you could call this my score, is 0.55. Finally, for the X class, I have 2 tests that involved the X class. This one gave me 0.97, this one gave me 0.99. You can see that in this case, my score is much higher. So I have a score for each of the classes. I choose the class with the highest score. Right? So this is a different procedure from when we're doing one versus many. So to summarize the procedure, create a series of binary classifiers. That is, take each pair of classes that are involved. Now, if you have, say, 5 classes, that means you're going to have 10 different pairs. So this way of classification involves developing many more classifiers than one versus many. Right? Now, each one of these binary classifiers is going to give me a probability. Okay. So when I have a new data point and I want to evaluate that data point relative to a particular class, I look at all the classifiers that involve that particular class. I get a score for that class from all of those classifiers. I sum up the score, and I'm going to get a score for every class. And the class with the highest score wins. Here you say total probability. Total probability is really not a good description because you're adding different probabilities, which does not necessarily give you a probability. So you should say the class with a maximum probability score. It's not really a probability. Now, when you're doing one versus one, you're going to have a lot of classifiers, as I said. If you have 3 classes, there are 3 classifiers. If you have 4 classes, there are 6 classifiers because there are 6 different pairs. If you have k classes, the general formula is 1/2 times k minus 1. So that can become very large. If you're doing 10 classes or 100 classes, this can become quite large. Now, what are the relative advantages of the 2 methods? One versus rest is the cheaper and simpler, fewer classifiers. Now we have this bullet point, more sensitive to unbalanced classes. Unbalanced classes means that some classes have many more instances than others. In the examples we've seen so far, all the different classes have had fairly equal numbers of instances in the given data. But you can imagine a case where one class may have hundreds of instances and the other class just has a few. And of course, that's going to favor a determination of being in the larger class. So that is an issue in classification when you have unbalanced classes. So this is a simpler comparison, but it can be less accurate. Now, one versus one is much more expensive computationally. You have to train more classifiers and you have to make more predictions. But generally, when you make more predictions, that gives more of an opportunity for cross-checking and cross-correction. Less sensitive to unbalanced classes, I think it's because you're making more comparisons between classes. So we have more chances of the classes having equal sizes. There are probably more sophisticated theoretical reasons for this. But these are basically the trade-offs between the two. Now, one approach is to try both and see which one works better in the situation that you're actually applying in. So let's stop here, and in the next video we'll talk about measures of classification schemes, ways of evaluating them and quantifying their performance. Now, of course, when we did logistic regression, we had to come up with a cost function But for the purposes of discussion or comparison when you're doing multiple classifiers, we need some method of representing how well that classifier is doing. And there are different ways of representing that. We'll talk about that in the next presentation.